Hello, this is going to be assignment 7, problems 8 through 12. So assignment 7 is actually 3 different videos here. But this is again assignment number 7, and I'm going to do problems 8 through 12 on this video. Okay, let's go see if I can share that. That worked well. Okay, problem 8, assignment 7, 30 GPAs from a randomly selected sample of stats students at a college are in the table. Assume population distribution is normal. Technician claim population mean GPA for whole college, so that's the claim or a null value, if you will, of 2.89 for the mean. A one-sided test with a significance level of 0.05 had previously been performed, and the null was rejected. Okay. Use the data to find a 95% confidence interval for the mean GPA. And then it says if a two-sided alternative had been used with a significance level of 0.05, would the mean have been rejected? Okay, so this is an important point here. We've got let's do a one-sided test here. Okay, so you can see this whole story. They're telling us it's been done, but let's do it ourselves. Okay. So I'm going to reread the problem. I got to figure out which alternative hypothesis to use for the one-sided test. Okay, 30 were selected. Assume it's normal. We have the mean value that's claimed. Okay, they don't tell us in this problem which one-sided test was performed. Okay, so they're just saying that a one-sided test with a significance level of 0.05 was performed and the null was rejected. So let's just arbitrarily do we'll pick one direction for the one-sided, and we'll look at what that situation is. So, and it said this one-sided test was done at alpha of 0.05. Well, I'm not sure if you see this screen that I'm seeing here, so let me. That's this screen. There, okay. I don't think you were seeing that screen, but this is the screen that I just read. So let's go in and do a one-sided test, okay? So, and let's say, again, so we're arbitrarily going to pick a side because this problem doesn't tell us which sided test was done, and it doesn't give us the sample value that ended up rejecting it. So it's just saying that that a one-sided test did in fact fail. So we'll set up a one-sided test and see what kind of values make it fail. Okay, and we'll just arbitrarily test the condition, the alternative hypothesis that the population mean is greater than 2.89. So we'll make that our alternative hypothesis. Okay, so let's go into StatCrunch here. Okay, StatCrunch. Oops, we got the famous oops error here. So we gotta try it again until it complies with our wishes. Okay, good, it's loading. So let me stop share, reshare. Now let's go into StatCrunch. Okay, good. So let's go stat. And this particular problem did not tell us anything about sample size. Let me see if I can go back and read that problem again. Problem 8. Oh, well, yes, it does. It gives us an accompanying table. So let me get that table up here. Okay, here's the table. So the table has a sample size in it. And we've got 3, and we've got, looks like we've got 30 data points here, okay? So we know the population distribution was normal, and we've got n equals 30, so we know we can do a z-test, okay? Because n's greater than 25, and we got a normal population, so we know we're doing z. I just pulled the table up here, and it shows the 30 data points, okay? I think you don't see that on your screen, but that's all I've done is I just clicked the icon to pull the table up. I think you're still seeing StatCrunch. So let's go back to StatCrunch. So we know we're doing a z-test. Let's look at the normal calculator, okay? Because if we set this to mean 0 standard deviation 1, then it is the standard normal distribution, which is the z distribution, okay? And that'll show us what we want to know for this 0.05 significance test of a one-sided alternative hypothesis that HA, that mu is greater than that mean value that they proposed, okay? So let's go to the normal calculator. All right, we're already set here. We got mean 0, standard deviation 1. So we know these are z-scores. And it said it was a one-sided test. And at the 0.05 significance level, compute. Okay, and I want to do, I said we're going to test, the alternative is that it's greater than, okay? So that would actually be the other tail from the one I've got shown here. So to get the other tail that has 0.05 probability associated in it, we'll put 0.95 here. Okay, now we've got this other tail. So here is the critical z value. Okay, so this is z for a one-tailed test. Okay, you know, usually in all these problems up to now, we were always doing two-tailed tests. Now we're doing a one-tailed test. So we know if we were doing a two-tailed test, well, this would say x would be between two numbers, and here this x is really a z, right? If we were doing a two-tailed test, we'd have this x would be greater than some blank number here and less than some other number here. And when we put the probability in out here, it would give us these two values. We would be in the between mode, and we would have plus and minus z star in this area, right? But since we're doing a one-tailed test, in this case, we only have the positive z star value. And notice it's a 95% confidence level, so we got 0.05 probability in this tail, and our z for that. So one tail, I'm just writing this down for myself, and z equals 1.6449. Okay, to 4 digits. Okay, and so our problem stated that at the 0.05 significance level, which we have here, our critical z is Z is equal to 1.6449 approximately, okay? So in this test, if we would get a Z value greater than 1.6449, then we would reject the null that the original population was what we said it was in the null hypothesis, which I think this problem was like 2.89 or something. It doesn't matter what the number is. We don't actually need to know what the actual null number is here because we've got this calibrated in Z. So we know the center of this is Z equals 0. And that relates to whatever the null value is, okay, which is an X value. But we know for this test, if our Z-score exceeds 1.6449, we're going to reject, which means you reject the null. So the null said that this mean was the claimed value, which I think maybe was 2.89, but whatever it was, we're going to reject it, whatever it said it was, because we're out here in this tail. If we get a Z score for our sample that's bigger than this one. And our problem says that a one-tailed test was run and the null was rejected. So that says our Z was out here in this tail somewhere, okay, which means our X was up here somewhere too, right? Because the scale is, X's and Z's on the scale, right? So we know our sample was quite a bit above the mean because it's past this critical Z star value, okay? So let's go back to the problem now. I wrote that down. So for the one-tailed test, our Z was 1.6449. That's our Z star, okay? Our critical Z, or our threshold. And if I can get back into the problem here, okay, there's the problem. Okay, and I want to get back and do another share operation so you can see that. Share, 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 where's it at? Where's the problem? Here it is. Okay, you should see the problem now. So yeah, our claimed value, our null value for the population mean, it was supposed to be 2.89. It says a one-sided test with significance level 0.05. That's what we just did. Had been performed and the null hypothesis was rejected. So we know that our Z star was bigger than 1.644, okay, or 1.6449. Okay, so now it says use the data to find a 95% confidence interval for the mean GPA, okay? Oh, okay, so here, well, let's do that. What it asked for, it says use the data and calculate a 95% confidence interval. Okay, so we want to put this data into StatCrunch. So I'll do that, open data in StatCrunch. All right, and now I want to reshare the StatCrunch. There, and where's the data install? Here it is. Okay, there's the data. It's in StatCrunch, right? And we want to do a 95% confidence interval. Well, all we need to calculate that interval is the data itself. The confidence interval is just X bar, which comes from the data, plus or minus the critical Z value, the Z star. Now, since we're doing a confidence interval, we're saying it's between two values, okay? So that is a two-tail situation. You're saying it's that the probability that you're between these two values is 0.95. That means there's a 0.025 chance that you're out in either one of the tails, right? And there's a 0.025 chance you're in the left tail, and also there's a 0.025 chance you're in the right tail. Okay, so it says to find this confidence interval. Well, we can just go to stat, and this is a z-stat because n was 30. Our sample size is big enough, and we had a normal population. We got one sample. We have the data. We got the individual data points. So we'll say with data. We select the data. Then we come down here and we just click confidence interval 95, and we say compute, and it gives it to us, okay? So let's write that down. Our confidence interval, this is a 95% confidence interval. Lower limit is 2.9859, upper limit 3.2468, okay? There's our interval. And we have our standard error there. I'm going to just jot that down. Standard error. This is of the means, right? Of the sampling distribution of the means. It's the standard deviation of the X bars. That's what standard error is when you're talking about means. And it's 0.0665. Okay, we know the n was 30. So I just jotted this information down. Let's go back to the problem, and I'll see if I can reshare the problem. And it should be right here. Okay. Use the data to find a 95% confidence interval. Okay, we've done that. So it wants us to report it. How many decimals does it want? It wants 2 decimal places. So I'll just enter my confidence interval numbers here. It'd be 2.99, 2.99, 2, and the upper limit is 3.25, 3.25. Okay, and we don't need to look at that data anymore. Get that off of there. Check answer should be correct. It is. We continue. Next, test the two-sided alternative with significance level of 0.05. Determine the null and alternative hypothesis. Okay, the null is, it never changes, right? So as a technician in charge of records claim that the population mean for the whole college is, so it's telling us the value for mu under the null hypothesis. The null hypothesis means when we test our sample, there's no change from the real big population. So, you know, that that our sample actually came from a population that had the claimed value for a mean. That's what it means. Anyway, that's our null hypothesis mean, and you write that mu, the Greek character mu, with a subscript 0, it'd be mu naught, they call it, right, is equal to 2.89. They don't use the naught in their notation, but they say HO, which is the null hypothesis, and then they say mu. So we're looking for mu equals 2.89. We've got it here. We've got it on B and E and C. So, but now it says if it says test the two-sided alternative. Okay, so the two-sided alternative means the alternative is going to say mu is not equal to, because that means it could be out in either tail, right? That's two-sided alternative. So our answer here is going to be E, because we've got the null mu is equal to 2.89. The two-sided alternative is HA is that mu is not equal to 2.89, right? A one-sided alternative would either say mu is greater than 2.89, or it would say mu is less than 2.89. But a two-sided alternative is going to say mu is not equal to it. So that'll be the right answer. We'll move on. It likes it. Okay. The test statistic is, so how do we calculate our test statistic? Okay, there's a formula, and we know we're doing z-test. So our test statistic, z, is equal to x bar minus mu naught, our null mean, our claimed mean, right, divided by the standard error. That's our test statistic. And we wrote down the standard error when we did this a while ago and got that report from the confidence interval. So we already know what that is. So we can just plug this into a calculator. You have, again, it's X bar. Okay, now I didn't jot that down earlier. So let's go, let's get that again. So here's the table. I'm going to put the table in StatCrunch again. Excuse me, I'll just run the same report. I should have jotted down X. Oh, I got to reshare this. So stop share, reshare, select it again. That's over here. Yeah, okay. So stat. And this was a Z-stat. It was a one sample. It was with data because we actually got the data. We select which column the data was in. It was in column 1 there. And then we tell it, yes, we do want to do a confidence interval, and it's a 95% confidence interval. We say compute. There's a report we had a while ago. Okay, so I guess note to self, next time you're doing this, go ahead and write down, this whole little report here. In sample mean, standard error, lower limit, upper limit, or you can, minimize it and keep that alive on your computer somehow. If you can just get back to that window again, right? But so anyway, we did this because we needed to know what X bar was. So again, we're calculating the test statistic, okay? And statistic means it comes from the sample. And why does Z come from the sample? Because to get this Z value, we take X bar, which is the sample value, minus the claimed mean, which is a known value already, divided by the standard error. And the standard error is estimated from your sample also, right? It's the sample standard deviation divided by square root of n. So that's an estimate of the true standard error, and that comes from the sample. So anyway, we just do this in our calculator. So I got a calculator here, and I'm going to say X bar 3.1163 minus, use of not, I believe it said was 2.89. Let me see, I should be able to pull that up there. Yeah, that's right. Minus 2.89 equals, divided by the standard error, which I wrote down, of 0.0665 equals. So our test statistic, which will be our Z-score, if you will, is 3.403. Okay, 3.4030. That's our test statistic. Let's go back to the problem. I got to reshare screens again here. Stop share. Yeah, okay. It says type in the test to 2 decimal places. So that's going to be 3.40. Check answer. Okay. Likes that. Now it wants to know the p-value. Well, the p-value we can determine just from the test statistic and the confidence level we're testing at. Okay, so all you need to calculate p-value is to know which confidence level you're testing at, and also know what your test statistic is, which we've got both of those. Now you also need to know, are you doing a two-tail test or one-tail, right? Because that p-value is different depending on if you're talking about two tails or you're talking about one tail, because the two tails share the extreme probability, right? one tail contains the whole extreme probability in it. So anyway, let's go get the p-value. So we're going to go back to StatCrunch again. And I'm going to share this screen with you. Back in StatCrunch. Okay, we don't need that. Now there's two different ways you could get p-value. You could go stat. We know we're doing z-stats. One sample with data. We've done that before, right? This looks like what we did to get the confidence interval. But now, instead of doing a confidence interval, we're going to say hypothesis test, because that's going to give us a p-value as part of this report. But now when we do the hypothesis test, we have to tell it what the null hypothesis is, because it doesn't know that, right? That information's not in our sample. We have to tell it what the null value is. And so here it was 2.89. So 2.89. And then we ignore this confidence interval portion. And we do have our two-tailed event here, right? We've got HA mu is not equal to 2.89. So this tells it, okay, we're doing a two-tailed test. You say compute, and notice here we're given p-value on this table. We're also given, and we could have done this, I guess. So I gave you the formula to calculate your test statistic. And this is another way you could get the test statistic, right? When you do the hypothesis test, it produces your test statistic for you and a p-value. So if you just need the test statistic and you've already got all the numbers that go into the formula, it's very easy to just type that in a calculator and you're done. But I guess it depends on what you need. If you want the test statistic and a p-value, you get them both at the same time when you do this hypothesis test, okay? Just remember to enter your null mean value when you do the hypothesis test, because it can't calculate, it cannot calculate, I have to think about this for a second. Yeah, it can't calculate your test statistic unless it knows what the actual value of the null mean is, okay? You can calculate the critical z without knowing what the null mean value is, because critical z has nothing to do with what the claimed mean is. The critical z value only has to do with the normal curve and what confidence level, which kind of represents a probability you're talking about. That gives you a z star. That's a threshold value that you're going to use to compare things against. And so all you need for that is just the confidence level, and then you look up z star based on your confidence level. You don't need to know anything at all about the sample to get z star or t star for that matter, right? They're both critical values. But your test statistic comes from the sample, and this hypothesis test calculated our test statistic for us, okay? And to calculate the test statistic, remember it's got the value for the null hypothesis mean in that formula. That's part of that formula. It's x bar minus mu sub naught, right, divided by the standard error. So when you run your hypothesis test, you have to tell it what the null mean hypothesis value is. Okay, so to get your test statistic, you got to know the null value of the mean. To get your critical statistic, you don't need to know that. All right, but anyway, so we've got p-value here. I'm going to jot this down. Now the z it got was 3.4013, And mine was slightly different. And the reason is it's using more digits in its calculation. I got 3.403. It's got 3.401. So very slight difference there. But I think the answer, it just wants 2 digits. So we would have the same, we've actually got the same first 3 digits. Our z-stat we calculated from the formula, and this is z-stat. And let's write down the p-value, 0.0007. Okay. And what is p-value? Remember, p-value is the probability that you'll get a sample that's at the same z-value as your sample was. So you'll get that same value, or you'll get something more extreme than that. And more extreme means further away from the null mean than your sample was. That's what more extreme than your sample is. Because all of this is about how far your sample is from that proposed mean. And so when you get z-stat, that's a z-score, that's giving you the distance you are away from that's how many standard errors you are away from that proposed mean. And the p-value is the probability of getting that value for a z, or a number even bigger than that, that's even further away. So it's the probability that's in that tail of that distribution. Okay, that's what it is. So let's go back to the problem. And it says the p-value is to 3 decimal places. Well, if I round 0.0007 to 3 places, I get 0.001. Okay, it likes that. Okay, now interpret results. Since the p-value is, okay, so here's what when you do a hypothesis test, there's 2 ways you can do it, and they both give you the same answer, okay? If you know what z star and you know what your test statistic z, we'll call that your z score, okay, which is your sample z. So if you know z star and your sample z, okay, if z star is a positive number, then if your sample z is bigger than z star, you're going to reject the null because it's saying it's more standard errors away from the mean than that critical value was. So you reject, right? If it's a negative number, if your z star is a negative number, then if your sample is more negative than that, like if say if z star was minus 2.2, if you got a bigger negative number like minus 2.8 or minus 3.0, that's further away from the mean than the minus 2.2, you're going to reject. So in either case, it's a bigger number than z star, whether it's positive or negative, right? But that's that you can do the test if you just know those 2 numbers. If you know what the critical statistic is, z star, and you know what your test statistic, which is the z score for your sample. You compare those 2 numbers, and if your sample's bigger than the z star, you reject. If it's not, you don't. End of story. Okay, that's one way to do the test. The other way is if you know the p-value of your sample and you compare it to the significance level of the test. Saying what the significance level is, it's the probability that you'll get a z star, that you would get the value z star or something more extreme than z star. That's what the significance level is. So there's a when it's 0.05, there's a 5% chance that of getting the value that you got for z star or a value even bigger than z star, okay? Now, you go collect a sample and you determine the z-score from your sample. That's your test statistic. And there's a probability associated with that, right? The probability of getting the value you got for your sample or more extreme than that. So what the test is you compare the p-value for your sample which is it's the probability of getting a value at your sample value or further out into the tail than your sample is. You're comparing that probability with the significance level, because that's the tail probability for the Z star number. I'm going to switch the camera over and show you, like on a it's easier to see on a one-tail test. Okay, here's a one-tail test. So here's Z star. Well, I've done this. I think I've done this a couple times already on these films. I'm not going to do it again. I guess I've done it twice already. It's easier to see in the picture. Well, maybe I will though. So this is Z score, which is your test stat. Okay. Oh, I gotta move stuff to get it under this camera here, but I can do that. Okay, there you can see that. So if this is your critical, so let's say we're doing a one-tail test because it's easier to see if you're doing a one-tail. If you're doing a one-tail test, everything from this critical Z on out, this is, if you're doing at a 95% confidence level, in this area in the tail, anything beyond Z star is 0.05, okay? And that's called your significance level. All right. Your p-value is the probability of, now here's your sample, and it's out, in this case, when we got our sample, it was out past Z star. So this is the Z score from the sample, which is your test statistic, all right? Well, the probability from it on out into the rest of the tail, this is the p-value. That's what p-value is. It's the probability of getting a sample at the value you got or more extreme than that. So the test is compare p-value to the significance level. Okay? If p-value is less than the significance level, reject the null hypothesis, which says that the mean is whatever it was proposed to be. Okay, so you basically, if you get a sample that's out here past this critical value, your p-value is going to be less than the significance level, because this whole area is 0.05 from Z star out. So if I go past Z star, the area from there on out is going to be less than 0.05. That's why you say if p-value is less than significance level, you reject. You say, well, then this, you know, we don't believe that. If we get a sample that's out here, we don't believe this is the true value, that the distribution really lives right here where we said it did in this diagram. But if your sample hits inside Z star, then you cannot reject. But if your sample hits inside Z star, you can see your p-value, you're going to have more probability in the tail than you had for your significance level. This is going to be the probability. If your sample hit here, for example, your probability of getting this, let me drop it so you can see it better. Probability of getting this is, say, what your sample was. If you got this for a sample value, probability of getting that or something more extreme than that, more extreme means further away from the mean. Here's the proposed mean. So the probability of getting this or something further away, you know, is this whole tail here, right? It's this whole thing. Well, this probability is going to be bigger than your significance level because its probability didn't start counting until you got to here, right? So it's the area starting from here on out is 0.05, then the area from here on out is going to be more than 0.05. So if your test statistic p-value is greater than your significance level, that's just another way of telling you the same thing, that your sample was not past this critical z, right? So there's two ways of doing the test. You either compare the critical z with your test statistic z from your sample, your z-score, and that's going to reject or not reject the null, just depending on if your sample is farther out here, farther away from the mean than z star was, you're going to reject. That's one way of doing the test. The other way is to compare the p-value, which is the probability of getting your sample or something worse. So it's the tail from your sample on out. You compare that probability to the significance level. And significance level is the probability that you'll get a z star value that's at z star or something more extreme. And if we're testing at 95% confidence, that means this significance level is 0.05. So there's a 0.05, there's a 5% chance you'll get past z star. So if you compare p-value to significance level, you're essentially doing the same thing as comparing a test statistic z to the z star. It's two different ways of doing the same thing because they're both going to agree. If one fails, the other, they're just different ways to represent the same thing. On one hand, you're just looking at the location of this line if you're comparing the two different z values, but if you're comparing the probabilities, you're just comparing those two areas, this area versus this bigger area. And then, of course, both of those change depending on where your sample hits. If your sample hits inside z star, you're going to have a bigger probability of getting that. You're going to have a bigger tail area than what you had for the z star area. And so you're not going to reject because your p-value would be greater than your significance level. Also, your test stat, your z-score, is going to be less than z star if you hit closer to the mean. And if it's less than z star, you do not reject. So they both always give the same outcome. Okay, let's do the problem. Since p-value is, and in this problem, what did we have? We had a p-value of 0.001. Our significance level was 0.05. So we're way less than our significance level. So we have a value that's beyond our z-star. Our z-score for our sample is bigger than z-star. And you see that here too, because for a 95% confidence interval, we know for a two-sided test at 95% confidence, z star is 1.96. And here you see our sample z is 3.40. It's much bigger than z star. So you know you're going to reject already, but you get the same conclusion here. You compare this 0.001 and you say, is it less than 0.05? Well, yes, it's quite a bit less than 0.05. So you reject. Okay. Since the p-value is less than or equal to the significance level, we reject HO. There is sufficient evidence to conclude that the mean GPA is different than the claimed value. And that's a satisfying answer. Next question. Okay. 10 people went on a diet for a month. Weight losses are given below. Negative weight loss is a weight gain. Test the hypothesis that the mean weight loss was more than 0 using a significance level of 0.05. Assume population distribution is normal. Okay, now key word here on this test is we're testing not that it's different from 0, but we're testing that the weight loss was more than 0. So that's a one-sided test. That's a one-tailed test. So our alternative is going to be, the alternative hypothesis is going to be that the weight loss was greater than 0. Okay, that's going to be HA. So mu, the alternative is its population mean is actually more than 0. So mu is greater than the null hypothesis. Okay, so so the null hypothesis here is that mu is equal to 0. Okay, let's read it one more time. 10 people are on a diet, weight losses are recorded. Test the hypothesis that the mean weight loss was more than 0. So here it's just kind of inferred. It's not really stated, but from reading it, you understand, okay, there's this assumption that what we're testing is it equal to 0 or not? And the or not here, instead of just saying is it's either 0 or it's not 0, they want you to say it's either 0 or it's more than 0. So the null is that HO would be mu is equal to 0. The alternative hypothesis HA would be mu is greater than 0. And so we got to find that. Here it is in F. The null says, okay, the weight loss is 0. And the alternative says it's more than 0. So we're testing this diet to see if it works. Okay, and so the null hypothesis is that there's no effect from this diet, that the weight loss from this diet is null. It's 0. That is the null value. It's 0. Okay, and the alternative is that, hey, we do have some weight loss from this diet, and statistically we want to check this out. So F null mu is 0, alternative hypothesis mu greater than 0. And remember, mu is the population mean, right? When you do a statistical test, you're getting a sample in order to make a statistical statement about the population mean, about the big picture mean. And so from this sample of 10 people on this diet, we're wanting to make a statement about the diet in general. If everybody went on this diet, would there be weight loss or not? And the null hypothesis is no, there's none. That's the status quo. That's the claim, okay, or that's the assumption that if the diet doesn't work, the weight loss is 0 for anybody on this diet. And the alternative is that there is a positive weight loss. Okay, check answer. We're okay. The test statistic is, so let's calculate this. Now it gives us a table here, so let's put it in stat. Oh, you know what? I didn't share this screen with you. Let me go share this screen. Okay, where was that at? Was it here? Yeah, so here's the screen I've been talking about, okay? 10 people went on a diet. Okay, this is the screen, and here's the correct null, correct alternative. Okay, so now we're going to put the data in it wants test statistic, and let's go ahead on this one. Oh, now notice we've got 10 people, okay, and assume population distribution is normal. Okay, with 10 people, we know we're doing a t-test now because we have a small sample size, right? N's less than 25. We're not doing Z, we're doing T. It's very similar, but we have to know the degrees of freedom in addition to the confidence level to know what our T star value is supposed to be, okay? So it wants a test statistic, so let's open in StatCrunch. There's the data. I'm going to reshare. And here's the data. All right, and we go stat. So now we're doing t-stats, right? because we had a small sample size. We got one sample, we do have data, and it wants the test statistic. So let's go ahead and do the hypothesis test, and we can get the test statistic. Okay, now here, remember in this particular problem, because usually it's not, usually the null hypothesis mean value is some other number other than 0, usually. But it can be 0, just like it is in this problem. We're saying the null is that there's no change, there's no weight loss. We're measuring weight loss. And so the null value is 0 in this problem. And now notice we're not doing a two-sided test here. This says you want to do a two-sided test, but the problem tells us we're doing a one-sided test. It says that our alternative is that HA, we want to know, okay, either the weight loss is 0, there's no change for people going on a diet, or the alternative is, hey, mu, which represents the amount of weight loss, is bigger than 0. That's the alternative for this test, and it's a 95% confidence interval. We have to select a variable up there. I should have done that already. Okay, and then we're going to do hypothesis test, set HO to 0, make sure our alternative's the right one, or, okay, and we're good. Compute. Okay, so this gave us our test statistic, which now is a t-value and not a z-value, but it's the test statistic. That's the one that comes from your sample. Okay, so you could call that a t-score, right? It's 3.4125, p-value 0.0039, and I don't know what all the problem will want later, so I'll go ahead and jot down sample mean 3.8, standard error 1.1136. Okay. Degrees of freedom, that's always a sample size minus 1. We had 10 in our sample, so that's 9. Let's go back to the sample. Let's reshare it so you can see it too. The test statistic, and it wants 2 decimal places. That would be 3.41. 3.41. Okay, it likes that. P-value, we wrote that down. It wants 3 decimal places. So that'd be 0.004. It likes that. Okay, interpret. Since p-value it's less than or equal to the significance level, which is 0.05, right? Since p-value is less than significance level, we do reject. That means your sample's more unlikely than your critical t-value was. And we got our critical t from the fact that we're testing at 0.05. So we are going to reject. So there is sufficient evidence to conclude population mean. This is the thing we're testing, right? We got a sample, but we're testing to see if this population mean is more than 0 at this significance level. You always have to throw that in there, what significance level you're talking about. Okay, check answer. Good deal, Lucille. Okay. 10 of 12. Mean pulse rate is 69 beats per minute for a random sample 136. Then, okay, here's a pulse rate of that sample, and that gives us a standard deviation. Find the value of the test statistic, okay? Let me jot this down here. Mean pulse rate for adult males, so 69 is our null hypothesis mean. HO is that mu equals 69. And HO is always mu equals something, always, all right? So that's half the problem right there. And these, you know mu is going to equal something for the null hypothesis, HO, all right? For a random sample of 136 males, so that's our sample size in, 68.6 was the beats per minute for that sample. And it gives us a standard deviation, okay? Standard deviation is 11.1 beats per minute. All right, now notice for a random sample of 136 males, okay, so we're going to assume that the population's normal. Well, no, we're not. No, actually, we're not. Scratch that. We're not going to assume it's normal, okay? This problem doesn't tell you if the population's normal or if it's not normal, okay? So what's up with that? Okay, so usually, I mean, we like for the population to be normal because that lets us do, in some cases, better statistics, okay? That we can get tighter confidence limits, and we get to use the central limit theorem for one thing if the population is normal. Well, the population, it doesn't tell us here is it normal or not. Since it does not tell us, being a good scientist, okay, a scientist is skeptical, all right? So if it doesn't say, if we don't know if this population's normal or not, we have to assume that it's not. And here we don't know, so we assume it's not normal. So there's two cases if the population's not normal. If you have a large sample size and a population is not normal, you're still allowed to use the t distribution, the t statistic, and use the central limit theorem. That's the beauty of it, okay? If the population's not normal and you have a small sample size, you're done. You can't do any of these tests. And so we don't have that case in any of our problems. But in the real world, you have that case a lot of times. If you have a population, you either know it's not normal or you don't have evidence that it is normal, then you have to assume it's not normal. Okay, you're still all right to do these statistics if you have a large sample size in this case, okay, and in which case you use the t for your statistic. If your sample size is small and your population's not normal, you're done. You can't do z or t, you can't do anything, okay? And then the last case, which is nothing to do with this problem, but just to give you that general background knowledge again. If the population is normal, it's known normal, and you have a large sample size, then you use z. So that's really, when you're testing means, that's the only time you use z, is normal population, large sample size, and greater than 30 or 25, okay? Use z. So there's two cases that you use t. You have a normal population but small sample size, that's a t, or the opposite. You have a not normal population but you have a large sample size, you use t. And I draw, well, you can see this camera here. I'd drawn that up a couple times before, but population, normal, population, not normal, okay? And you got z, no, you got small sample size, and you got large. And small and large, you're just comparing it to 25, right? Small means n is less than 25, large n is greater than 25. So population normal, small sample size, use t, okay? Population normal, large sample size, z. Population not normal, small sample size, it's a mess. Can't do anything. You're done. Not normal, large sample size, okay? T. So you notice there's two times you can use a t distribution. There's only one case you can use a z. Population is normal and you got a large sample size, okay? What else was I gonna say? It seemed like there was something else there, but that's the gist of it. Oh, And this is with means testing, okay, where we're looking at population means and X bars. Means testing, okay. Population means, and we're getting X bar for our sample. That's when you have to think about this. The other kind of testing we do is proportions testing, right? And in proportions, it's different. There's three different conditions to be able to use the central limit theorem for proportions. But in all of those cases, if those conditions are met, you use the Z distribution for proportions, okay? If the conditions are not met, you're done. You can't use either one. So with proportions, if you're doing the test at all, if you're able and allowed because the conditions are met, it's always a Z test. With means testing, it might be it's more likely it's a T, but sometimes it'll be a Z. Now, Z is slightly simpler than T, right? Because T, we have to keep track of degrees of freedom. Z, there's only one Z curve, only one. So the Z star value only depends on your confidence level. You look up the confidence level, that tells you what Z star is, you're finished. With T, you have to know what degrees of freedom are before you start, because there's a different T curve for each degree of freedom. So you get the degrees of freedom, which is sample size n-1. And once you got that, then its value on that curve is determined by the confidence level, okay? So it works out pretty nice. But let's get back to this problem. So we said that, I think I wrote that down up here. Yeah, here's HO, the mean is 69. We got our sample size 136, and we have to assume the population is not normal here because there's nothing that says it is, doesn't tell us anything about it. And so because of that, but we have a large sample size, we're allowed to use the T distribution, okay? And then it gives us our actual sample with 68.6 beats per minute. It's X bar. And it gives us a standard deviation. And it says find the test statistic. So let's go to StatCrunch, our old buddy there. And I put a thing on Blackboard that says how to get, well, that's how to get T star. I put on Blackboard. This is the test statistics. This is the one from your sample. So it's not T star here. But let's, I just have to load. Oh, we don't have a table here. I think maybe if you go into settings, no. Okay. Sometimes I have an issue here because, or maybe it'll let me click on it. There, that's good. Okay, I'm gonna close that out. I'm gonna reshare StatCrunch with you. All right. There's StatCrunch. Select it. Now this was old data here, so I'll just delete it. I'm trying to delete it. Oh, okay. There we go. So that's from another problem, right? Okay, what it's asking us to do is get the test statistics. So let's just go ahead and do that hypothesis test, because we know we get a test statistic and a p-value from that same operation. So here we have one sample. Now we do not have data, right? It just told us that out of 136 people, it gave us the X bar, 68.6, but we don't have the individual results. So we say with summary, sample mean, it gave us that, 68.6. All right, sample standard deviation, it gave us that, 11.1. Sample size it gave to us at 136. Okay, and we're going to do a hypothesis test. And because of that, we have to tell it the null value. It was 69. And now also we have to check the alternative hypothesis. And this problem, let's go back and read it again. You can't see it, but I'll read it to you. It says, da-da-da-da-da, da-da-da-da-da. Well, it hasn't said what kind of test it wants yet, okay? The mean pulse rate for random sample mean. Okay, since it doesn't tell us what kind of test it wants, we have to assume that we don't have any prior knowledge about this. So we're kind of ill-informed researchers here if we're actually doing this right now. So if we're going to do a statistical test on this population mean of 69 to see if that's if we can support that or not, and we go get a sample, which test are we going to do? Since we don't have any knowledge, any pre-knowledge about any of this, we're going to do the two-tailed test. We're going to say we're just going to test, is it not equal to that, which means it could be way bigger than that or way smaller. In either case, we'll get a flag, right? We don't want to test, is this bigger than this, when in fact it might even be smaller than that. We don't want to be doing a test, is it bigger than this or equal to that, right? Because if we did that test and it was smaller than that, we just wouldn't be able to reject that it could possibly be equal to that, right? So when you have a lack of knowledge, you do the two-tailed test. So back into StatCrunch, and two-tailed test is not equal to compute. Okay, and I'll write down our t-stat, which is our test statistic, is minus 0.4202. Our p-value is 0.675. And I don't know what the rest of the problem was. I'll write down standard error, 0.9518. And the mean X bar, well, we put that in. We know what that is, okay? And we know what the degrees of freedom is. That's always just n minus 1. So let's go back to the problem. I got to reshare it. And here's the problem. The test value of the test statistic is, you can have a drum roll, please. And it wants 2 decimal places, minus 0.42 is what I get. Okay, and it liked it. Now, we can just look at our test statistic, okay? Now, we haven't calculated t-star yet, but think about what these are, what t-values are. They're t-scores, okay? So they're a count of standard deviations away from the mean too, okay? Actually, a count of standard errors away from the mean. And a standard error is the standard deviation of the sampling distribution, X bars, right? So what I'm getting at here is forget the negative sign for a moment, but the 0.42, the size of this, it's small, right? Standard deviations that start approaching a threshold or something you're going to, that possibly may go past a threshold are going to be around 2 something, right? Say from 2.0 and bigger. So if you get a big test statistic value, like, and when I say big, I mean like maybe greater than 2, or you start being concerned about it when you see 2, but a number bigger than that, that's considered a kind of a bigger value. It's more extreme. It's more standard errors away from the mean. Remember that empirical rule? 68% were within plus or minus 1 standard deviation. 95% are within plus or minus 2 standard deviations. So your test statistic, when it's a bigger number, is when it's going to fail, when it's going to exceed your t-star or your z-star value, right? It's when you get a big number. So my whole point here is this is a small number. we're not going to be rejecting anything based on this sample. So if we just look at what we had, the proposed mean was 69, we got 68.6 out of 136. That's not a whole lot of difference, right? We're only 0.4 off of what they're saying it is. So it seems reasonable we get a small value for this test statistic here. And it's below the mean, right? Negative, minus 0.42. Next question. Oh, it's actually another question. Okay, trap spacing measurements. That's a mouthful. In meters for a sample of 7 teams of red spiny lobster fishermen, something we all know a lot about, right? Maybe somebody does. There might be somebody with some experience in Maine or Alaska, but anyway, are reproduced in the accompanying table. Let mu represent the average trap spacings for a population. Mean and standard deviation are, okay, so it's given us X bar 90.6, and it's given S, it's a sample standard deviation 12.3. Suppose you want to determine if the true value of mu differs from 95 meters, okay? So 95 is going to be the null hypothesis value. HO, the null hypothesis, is going to be mu, and I like to say mu sub naught, right? Mu sub 0 there, subscript 0, okay, equals 95. And it says, suppose you want to determine if that differs from 95. So differs just means it's not equal to. It doesn't say. You want to determine if it's bigger than 95. It doesn't say. Do you want to determine is it smaller? So we don't know anything about this. We don't have any suspicions before we do this test. So we're just going to do the real general test. Is it different? So that's HA. Mu naught is not equal to 95, okay. Specify the null and alternative. So the null's mu's 95, the alternative is not equal. We're done. That's A. All right, so let's go to B here. Since 90.6 is less than 95, a fisherman, he notices that, right? The guy got the sample and he says, okay, here's my sample, 90.6, it's less than 95, so I want to reject the null. This fisherman says, well, then that 95 isn't right because this is a fair amount smaller than that, so I'm going to reject it. He says, what are the problems with using such a decision rule? So he's just using his general intuition, right? This is what he's testing. He got a sample. It's smaller. He says, okay, so what I'm testing isn't true. It is less than that. It says, so here's some problems associated with that. And A says, reject a null problem must specify sample size. B says, reject a null problem must specify critical value of T. C says to reject a null must specify the value of alpha, which that's your significance level, right? That's 1 minus the probability. That would be this 0.05 if we're doing a 95% probability confidence level, right? Okay, anyway, reject a null. I'm reading C. Reject a null, problem must specify value of alpha and a probability the test will lead to rejection, and then consult the T or Z table depending on the size of the sample. I'm going to stop right there because that's correct. To reject it, you got to specify what significance level are you testing at, because you can reject it at one significance level, but at another significance level, you might not be able to reject it. So rejection depends on which significance level you're talking about. That's very important. So you have to specify that. Okay, and that significance level gives you the probability that a test would lead to rejection. Okay, that's what that significance level is. It means that there's a 0.05 chance or 5% chance, a random chance that your sample would be in that rejection region, out in the tail, out in that 0.05 area where that tail is. There's a 5% chance it'll be past that critical value. That's true. And when you consult the T or Z table, that tells you what the critical value is that you're going to compare your sample to, and it depends on the size of your sample. Well, your test statistic depends on the size of your sample, okay? The critical value doesn't depend on your sample size. The critical value just depends on the significance level. That's the probability that the test will lead to rejection. And then you consult the T or Z table or technology, okay, to get your test statistic. And your test statistic is a function also of the sample size, right? Because it's divided by the standard error, and standard error has sample size in its calculation. So C is the right answer. Let me see if I can scroll down here. Compute the test statistic. So we got to do that. Okay, let's compute a test statistic. We'll send this to StatCrunch and share it. So here's this trap data in StatCrunch. And again, let's do the hypothesis test, because that seems like that gives us more, unless it's specifically asking for a confidence interval, we get more information out of the hypothesis test than we do when we click confidence interval, depending on what you're looking for. But you get a p-value and the test statistic out of the hypothesis test, all right? So I'm just refreshing myself. Okay, so 95 is the null mean. Our X bar is 90.6. We got a standard deviation. So let's go stat. Oh, we got to determine, are we going to use T or Z, right? Let's look and see what it says. Oh, well, our sample size we've got here in this table, 3, 4, 5, 6. Our sample size is 7. They went and got 7 traps and looked at them. That's a small sample. So we know we're doing a t-stat because it's a small sample. T-stats, one sample, we have the data. We're going to do, we got to select the data up there, move it into that column. We're going to do the hypothesis test, so we have to enter the null value. 95 is the null value. And we're doing a two-sided test, so we're done. We say compute. We get a t-stat of minus 0.9505 and a p-value 0.3786. Okay, X bar 90.5714, standard error 4.6591. That's good enough. All right, let's go back to the problem. Let's stop share, and okay. We're going to scroll down. Said calculate the test statistic round to 2 decimal places. Okay, 2 decimal places would be minus 0.95, minus 0.95. Okay, we're good there. Find the approximate p-value to 3 decimal places, 0.379, 0.379. Okay. And select the value of alpha. Select a value of alpha, the probability of a type 1 error. Okay, so the significance level, this is other terminology that they're introducing here, but it's true. The significance level is the same thing as your type 1 error rate. So what's a type 1 error? Type 1, here's what a type 1 error is. Let's say you're testing some hypothesis, okay, and so that you've stipulated some mean value for the population and you want to test that. Well, let's take the case that that's actually true, that is the mean value for the population, okay? So let's say we somehow we know that, all right, but that actually that's true, okay? So it's a hypothesis, but we're saying in this case it is true. We know that is in fact the case. So now you do this statistical test that we've been doing here repeatedly, right? And say you get something out in the tail region when you do your test. You get something that's a really low probability event, right? Well, when you get that result, the rules tell you that you have to reject a null. So we get this. So here we've got a null that we happen to know secretly that null really is true. But we did our statistical test and we got this very low probability event that tells us we have to reject the null based on the statistics, okay? So what's happened there? We've committed an error. Now we didn't, now in this case, we know it's an error because we know the real nulls actually really is true. But when you're doing a test, that's what you're doing. You're testing to see if it's true or not. And you don't know for certain if it's true or not. That's why you're doing the test, right? And so you get this result, and the result would tell you to reject it, okay? But in this case, we just set up secretly. We knew that it was in fact true, but we got this rare event that said to reject it. So what happened? Well, we made an error, and that's an error you would make, okay, that anybody would make because you have to follow these statistical rules. So that error you made is an infrequent thing that happens because most of the time, if you get a very rare event, the null hypothesis actually is not true. And you should be rejecting it, okay? So the rule says you reject if you get this really rare event. But just know when you do that what that significance level means then is there's a 5% chance that if you reject it, that you're actually wrong. And you don't know 100% whether you were wrong or whether you weren't wrong. You actually don't know that. Statistically, when you reject something at the 0.05 level because your sample was way out in the tail, statistically, when you do that, 95% of the time, you're going to be correct. You should have rejected it. So that's a pretty good success rate, right? If you're right 95% of the time. But 5% of the time, you will be wrong. And you don't actually know when you offer up your result, was this one of the results in those 95% of the cases where I'm right, or was this one of those few rare ones where I actually was wrong? You don't actually know that. And that's why repetition is really important in science, right? You do a statistical test. If it's concerning something that's very important, like say you're testing a vaccine for whether it lowered the death rate or something of that nature, and you get this and you reject some hypothesis, it stands to reason that if it's a life or death thing that's going to affect a lot of people, what would you do? You'd probably run more tests, right, to have more confidence in your result. And actually, you'd have like other labs run that test, right? So you have independent results. You have independent testing by different facilities. And then you look at all those results together and they paint the true picture, right? and then the statistics start becoming even clearer, and you gain information about error rates and that sort of thing. So let's go back to the problem. Select a value of alpha, the probability of type 1 error. So your significance value that we keep talking about, which is 1 minus your confidence level, is the probability that you're going to make this error, which is you reject the null when really you should not be rejecting it. That's what a type 1 error is. So when you reject the null, effectively you're saying, hey, there's an effect here, okay? And type 1 error means you're confirming some effect that really isn't there because the null was true. So that's called a type 1 error. There are type 2 errors in statistics as well, but I'm not going to get into that right now, okay? So your significance level is your type 1 error. So it says, interpret this value. In other words, there would be sufficient evidence to reject the null if alpha were greater than 0.001. So here's our p-value. This is a big number for p-value, right? And so remember what the test is. You compare p-value to significance level. If p-value is less than significance level, you reject. End of story. It's as simple as that. So we got this 0.379. It said, what if alpha were greater than 0.001? Well, that doesn't make a lot of sense because how much greater, it doesn't say. That's too vague. Same thing here. So let's jump to see. There would be sufficient evidence to reject it if alpha were 0.001. No, there wouldn't, because this is not less than this. To reject, p-value has to be less than alpha to reject. So that doesn't make sense. D, there would be sufficient evidence to reject if alpha was less than 0.378. That's true, right? Because then if alpha, oh, wait a minute, let's see, there would still be evidence to reject if alpha was less than 0.378. No, you're not going to reject with a p-value of 0.379. Okay, it would be B here. There would be evidence to reject if alpha is greater than 0.378. So what they're saying there is if alpha is greater than 0.378, it's going to be either equal to your p-value or alpha is going to be greater than your p-value. And remember that the test is p-value less than alpha? When p is less than alpha, you reject. Okay, so if alpha is greater than 0.378, then p-value is either going to equal alpha or p-value is going to be less than alpha. And at a p-value equal to alpha, you can reject, okay? So that's the rule. When p-value is equal to or less than alpha, you reject. So if alpha is greater than 0.378, our p-value would be equal to alpha, or it would be less than alpha, depending on how much bigger alpha is. But it's either going to be equal to alpha or it's going to be less than alpha if alpha is greater than 0.378. So B is the answer. Check answer. Okay, next. Interpret. Type 1 error would be to conclude its true mean is 95 when in fact the mean is equal to 90.6. Okay, so the null was 95. A type 1 error is you're going to reject the null. Okay, but when you do that, you're making an error. That's why they call it an error. So type 1 error says you've rejected the null when you should not have rejected the null, okay? So when you conclude the mean is 95. Well, no, you're not concluding it's 95. That's the null, because if you're concluding it's 95, you're not rejecting it. And to commit the error, you're rejecting it when you're not supposed to be. So concluded true mean is 95 when it in fact is not equal to 95. No, that's wrong. Type 1 error would be conclude true mean is not 95 when in fact it is 95. That's the one, right? It's an error because you're rejecting it. So you're concluding that it's not 95. That's rejecting, because they're claiming it's 20, they're claiming it's 95. And you're concluding it's not 95. So you're rejecting that 95, okay? But in fact, the mean really is 95. So when you reject it, you're making a mistake. And here you are rejecting it. And in fact, when you do that, you're wrong. So that is a type 1 error. And the significance level is the type 1 error rate. There's 5% chance you're going to do that when you test it to 0.05 significance level. So C. There is a method to this madness. F, this is a long problem. Give the appropriate conclusion based on the results of D and E. Let alpha equals 0.05. So what was D and E? We got to scroll back up. D and E. There's E. There's sufficient, okay, D. All right, our p-value is 0.379. That's our p-value. That's probably all we need. P-value 0.379. Oh, and it said, well, it said D and E. And E said, it was this weird case of saying, say alpha, say our significance level was greater than P, basically. That's what this comes down to, yes. So we'll assume that our p-value is less than alpha, okay? Because they're saying alpha is greater. Essentially, it's going to be greater than or equal to our p-value. And when p-value is less than or equal to alpha, which would be true in that case, we're going to reject, okay? So we have the case here. If alpha is bigger than this or equal to this p-value, we are rejecting. That's all we need from that. So we know we're rejecting. There's two answers that say reject. And when you reject, what is it we're rejecting? We're rejecting that the mean's 95. So it says reject, and it says there's sufficient evidence to indicate mu is not 95. True. We're rejecting it because our sample statistics are indicating we're supposed to reject it. So there's sufficient evidence based on our sample statistics that it's not 95. Check answer. Okay, it doesn't like that for some reason. So what's going on there? Reject, give the based on, oh, I see what the issue is here. Yeah, it doesn't make any sense. They said based on results of parts D and E. Okay, well, forget this E business. No, it's not based on E, because that would be the answer I gave. We just ignore this E here. So we do pay attention. Here's the p-value. That's the critical thing. But then they said based on D and E says that alpha is greater than this. But down here in the problem, they say let alpha equal 0.05. Well, if alpha is equal 0.05, E has nothing to do with it anymore, because that's all E said, that alpha was greater than was basically greater than P. But here they're telling you a different number. So you will go by the number they're giving you in this problem. Alpha's 0.05. Our p-value was 0.3 something, which is way bigger than this. So ignore, that's a mistake when they say based on D and E. It should be based on D, yes. You should always look at your p. That E was some hypothetical thing they wanted you to look at. But D is what our actual p-value was, and they're saying, okay, let's say we're testing at 0.05, where p is way bigger than alpha, so we're not going to reject. Okay, so fail to reject, and we're going to fail to reject because there's insufficient evidence to indicate that it's not equal to that. We can't say it's not equal to that because we don't have sufficient evidence to say that. So there is insufficient evidence to indicate it's not equal. So it's D. All right. Part G, what conditions must be satisfied for it to be valid? Trap space, okay. Okay, we need a random sample. It's selected from the target sample. No, that's talking about a sample from a sample. We're not doing anything like that. Conditions must be, random sample must be selected from a target population. That's true. And the population from which the sample is selected has a distribution that's approximately normal. That's true. Okay, in this case, in this sample problem, the population has to be normal because we have a small sample size, okay? If we don't have a normal population, and we know we have a small sample size here, we can't do the test. So B is the end of the story there. We got to have a random sample from the target population, so it needs to be a representative random sample. And population from which it's selected has to be approximately normal. That's true because we have a small sample. If we had a large sample size, population wouldn't have to be normal because we could still do these statistics using the t distribution, the t-test. But here, so it's B. Okay. I'm amazed. We're up to H here. There's a lot of parts in this problem. It's given us the confidence interval. Does the interval support our conclusion? Well, what was our conclusion a while ago? Our conclusion was that we had insufficient evidence to reject it. That was our conclusion. Okay, and what are we testing to see if it's 95? Is that inside this interval? Is 95 between 79.2 and 101.9? It is between them. So it's in this, the null hypothesis mean is in our confidence interval. That's going to support our earlier conclusion that said we do not have evidence to reject it. If your proposed population mean is inside your interval, that's saying, hey, you don't have sufficient information to say it's wrong. It has to be outside of that interval for you to say, nah, statistically, it probably ain't happening. Okay, final check. Ta-da. Okay, last problem. Summary statistics for 27 students who completed a dental anxiety scale questionnaire. X bar is 10.7, that's X bar. S, sample standard deviation 3.0. Scores range from 0 to no anxiety to 20 extreme. Conduct a hypothesis to test whether the mean value differs from mu equal 11. So HO, null hypothesis, mu equals 11. It says test to see whether it differs from that. So HA is going to be mu not equal to 11. Okay, and that's A in the first part of this. HO mu equal 11, HA mu not equal to 11. Two-sided test. It says the test statistic is, and here we don't have data, okay, but we could do our formula. Now, we have 27 students, so that's a large sample. It's greater than 25. And let's read here. So, doesn't say anything in this problem about a normal population. So we have to assume the population is not normal because we don't have sufficient information here to say, okay, we got a normal or approximately normal population. Nothing in this problem tells us that. So we have to assume it's not normal. So even though we got a large sample size, we still got to use the t distribution because the population is not normal. Okay, so we know we're doing a t-test here. When it says test statistic, it's a t, and it wants the value of it there. So the formula for that, you can see this over here, is t is equal to x bar minus mu naught over the standard error of the x bars. That's what t is, okay? The test statistic. And we've got x bar 10.7 minus mu naught. It says test to see whether it's equal to 11. So mu naught is 11 divided by standard error. Now standard error we got to calculate, but it gives us a sample standard deviation. So standard error equals the square, or equals s over the square root of n, okay? And it gave us both of those. S was 3.0 and n was 27. So 3.0 over the square root of 27, that's the standard error. That's what we put in the denominator. So that's one way we can do the test statistic. We could also go into StatCrunch and tell it to do a hypothesis test, and it calculates that, right? So let's do that. To open up StatCrunch, I think I'm already in it there. I'm going to close out some of this stuff. Stop share, reshare. Okay, and this was just junk data over here, right? There. Get rid of that. You don't have to get rid of that because we're not going to tell it to use this data anyway, but just being paranoid, not taking any chances, right? This computer might use something we don't want it to use. We might forget that it's there. But anyway, we're doing t-stats, one sample. We don't have data. We just got summary information. So we give it our sample mean, 10.7. 10.7. We give it our sample standard deviation was 3. We give it our sample size was 27. And hypothesis, we got to tell it what the null mean was. It was 11. And two-sided test here. I think it said conduct a test to determine whether it differs from u equal 11. So yes, two-sided test. All right, and we're back here. We got everything in. So we say compute, and notice our t-stat, our test statistics, minus 0.5196, p-value 0.6077. So we know from looking at either one of those two that we're not going to reject. That's not a big number for a t-stat. That is a big number for a p-value. So remember, we compare p-value to significance level, which was, 0.05, and this is way bigger than that. So we're not going to be able to reject. And this is going to be much smaller than whatever the t-star that we get for 95% confidence level is, okay? All right, so let's go back to the problem. And it wants us to put, I didn't write that down. Let me write it. Yeah, I did. I just didn't label it T. Okay. So let's go share. Yeah. Okay, test statistic is minus to how many decimals? 2, minus 0.52, minus point. I got to click in there first, I guess. I thought I did minus 0.52. All right. find the rejection region, okay? So that means we find T star. So this T that it's talking about here is the critical value of T. It's the T star value. We get that from the degrees of freedom and from the confidence level, okay? And it's telling us we're testing at a 0.05 significance level, and we're doing a two-tailed test. So we can use a T calculator to get this number. Let's go to StatCrunch. Close this, share the screen. Okay, we can go into Stat Calculator and T. Okay, see that? Stat Calculator's T calculator. We're wanting to get the critical value of T. We're wanting a T star number. So it's a two-tailed test, so click on this between. Let me raise this up in the screen here. Degrees of freedom, our sample size is 27, so degrees of freedom is going to be 26. And our significance level was 0.05, so I'm going to put 0.95 in here and hit compute. Notice it gave us these numbers, but see what we've got here? So when we're at a 0.05 significance level, that means the area in these two tails add together to 0.05. So there's 0.025 in each one of these tails. All right, but I put 0.95 here because the way this calculator works is it always tells you the probability that you're between these two. It gives you the probability, which is the area of the red shaded area. But what we want for a 0.05 significance level, 0.05 means there's the area of this tail plus the area of this tail is 0.05. So this is another way to get the same thing, right? Because you can think of this as your confidence level. So 95% confidence level is a 0.95 confidence probability. And that is that you're inside these, and these would be T star numbers, right? Even though it says X up here, we're in a T calculator, and we gave it degrees of freedom, so we know we're talking about T values here. So this is the critical T star 2.0555, and it's symmetric, so minus T star, right? Minus 2.0555. So minus 2.0555 and plus it. So let's go back to the problem. And they rounded it to 2.056. So the rejection region is the region where you're more extreme than that, okay? And since it's a two-tailed test, that means you could be outside the value on either side. So it's going to be one of these with two values. It won't be a single case, right? And it means that you'd be less than, and this means a bigger negative number than -2 if you're less than this, right? If you're less than, like, for example, -3 is less than -2. So that's more extreme than this, right? This is 2 standard deviations below, or 2 standard errors below the mean. If I had a T of, say, -3, that would be 3 standard errors below the mean. Or T is greater than 2 standard deviations above the mean. So this T is talking about here is actually your test statistic, your sample. Or wait a minute, let's see. Yeah, is blah, 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 blah. Oh no, I'm sorry. Find the rejection region. So this is T star. It means if your sample T exceeds this T, it is what it is, okay? So if your sample T, so this is the T value, this is the T star value, and this is your sample T here. Okay, so they're both here. Yeah, the number is the T star is the critical value, and the T, where it's just got the symbol T, that's your sample T, your test statistic T, okay? And again, it's if you have a more extreme value than T star, more extreme being further away from the mean. So if you're at less than -2, you're further from the mean than -2 is, or if you're greater than +2, you're further from the mean than this critical value. So it's C. Check answer. We like that. Select appropriate conclusion, okay. Are we going to reject it or not reject it? Okay, we had a small t-value and a high p-value, and both of those say, remember our t that we had was minus 0.52. Well, 0.52 is actually bigger than this. It would be, it's not less than -2 something. Our sample is more than this, but it's way less than this. So we're in that red, if you remember that red region from StatCrunch. We're actually not very far from the mean at all with our sample. And so that also gives us a high p-value, right? So, and to reject, our p-value has to be smaller than 0.05. And our p-value we had was 0.61. Well, that's way bigger than this. So we're not going to reject. Okay, so since we're not going to reject, and it's based on our statistics, it's saying that we have insufficient evidence to reject. We can't reject it because we don't have the evidence to reject it. So final check. You like that. And hey, we're done. Thank you very much for listening. I'm going to upload this, and you guys will have a day or two to look at this if you'd like. Your final, you can start scheduling it for Monday, Tuesday, or Wednesday. Have a great day. Adios. Let's go back into here. Stop recording.